Now the unit number 2, current electricity. In that, the first one is the electric current. It is the rate of flow of charge through any cross section of conductor. It is expressed as current is given by rate of charge of flow of Q. So Q by T, that will be the current, and Q according to quantization of charge. Q is equal to plus minus Ne. So from here we can replace this Q by Ne by T. Current always flows in the direction of flow of positive charge, and this flow is opposite to the flow of the negative charge. Another thing is that it is a scalar quantity. Scalar quantity means if you want to add the current, then it won't follow the vector law. Simply like numbers, you can add or subtract the current. The SI unit is ampere. It is after the name of scientist, and it can be denoted by capital A. The next is current in terms of drift velocity, and that will be equal to I is equal to NEAVD, where N is the number density of free electrons, E is the charge on electron, A is the area of cross section, and VD is the drift velocity of the electron. Then another term is the current density. It is denoted by J. It is the ratio of current to area. And if we write down I, NEAVD, so A cancels out and the current density will come out NEVD. It is a vector quantity. See, current is a scalar quantity, but the current density is a vector quantity because here the area is having the direction, though area is a scalar quantity, but in this case we have to specify the area with the direction. So this is the reason the current density is a vector quantity, and its SI unit is ampere per meter square. Now in the fourth point, we are talking about the mobility of the charge carriers. It is denoted by mu, and it is the ratio of the drift velocity to the electric field. Putting the value of drift velocity in electric field, that also comes out to be equal to Q tau by M, where tau is the relaxation time. Relaxation time is the successive time between two successive collisions. The unit is meter per second per Newton coulomb. See, in the drift velocity, meter per second is the unit of velocity, and electric field is having the unit Newton per coulomb because it is in the denominator, so that is why it will Newton per coulomb. Ohm's law. At a constant temperature, the potential difference across the ends of the conductor is directly proportional to the current flowing through it. So summing up this definition, we have having potential is directly proportional to the current, and when we take out the sign of proportionality, R comes here. R is the resistance of the conductor. Now the resistance of a conductor depends upon the length directly and upon area in the inverse proportionality. When we take out the sign of proportionality, rho comes here. Rho is a constant. It is called specific resistance or resistivity. The unit of resistance is ohm, and this is the symbol for it. Next is the relation between the resistivity and the relaxation time. So rho is equal to M in E square tau. M is in the numerator, Ne square tau are in the denominator. As you can see, the rho depends on the nature of material and temperature only. It doesn't depend on the length or the area. The SI unit of rho is given by ohm meter. That can be taken from here. Ohm is the unit of resistance, length is having meter, and area is meter square. From here we can conclude the unit of resistivity, ohm meter. Next is the relation between the current density J, electric field E, and conductivity sigma. This conductivity sigma is the reciprocal of resistivity. So we have the current density is equal to conductivity into the electric field. Conductivity reciprocal of resistivity. Its unit is just reciprocal of resistivity. The resistivity was having the unit ohm meter. It is having ohm inverse meter inverse. Ohm inverse can also be written as mho, meter inverse. Next is the temperature coefficient of resistance. If suppose the conductor is being having change the temperature, then alpha is the coefficient of the resistance, and it find that with the change in the temperature there is the change in the resistance. So initially if R1 is the resistance and T1 is the temperature, and after changing the increasing the temperature, R2 is the new resistance and T2 is the new time, then this alpha temperature coefficient is given by R2 minus R1, in the denominator the initial R1 and the difference of the temperature. This thing can also be changed by the resistivity too, because R is having the relation with resistivity, R is equal to rho L by A. So in terms of resistivity also, from that formula it can be derived. The next is the electrical energy. It is defined as the total work done by the source of EMF, electromotive force, in maintaining the electric current. It is given by E is equal to VIT. This is the basic formula. Now V is equal to IR according to Ohm's law. So according to that, VI can be written as I square R, or it can also be written as V square by R. So depending upon the numerical, if only voltage and resistance is being given, no current is there, then again you can find out electric energy and so on. The unit is, because it is an energy, the unit will be joule. Electrical power, it is the rate of change of electric energy supplied per unit time to maintain the flow of current of the conductor. It is given by P is equal to VI. Basically, power is equal to the electric energy upon time. So VIT is electrical energy divided by time, it will be VI. Now you can replace it with applying Ohm's law. It can also be written as I square by R. It can also be written as V square divided by R. And the SI unit of the power is watt. Next is the electromotive force. This is the source of energy that maintains the continuous flow of charge in the circuit. It is denoted by E, given by the work per unit charge, and the SI unit is volt. Internal resistance, it is denoted by small r. It is the resistance offered by the electrolyte of the cell due to the motion of charge through it. Next is the relation between internal resistance small r, external resistance capital R, electromotive force E, and the potential V. So internal resistance is equal to external resistance in the bracket electromotive force to the potential minus 1. So this is the how you can find out the internal resistance. This is during charging of the cell, the voltage or the potential can be given by the electromotive force plus the current into the internal resistance. So this is the circuit for the same. If potential or the voltage across is less than electromotive force, it means the current is being drawn from the cell, or the discharging of the cell is going on. If the potential is greater than the electromotive force, it means charging of the cell is being done. Next is the combination of cell. If the series combination is taken, the electromotive force equivalent is equal to E1 plus E2, that is, say 2 cells are being used, and the equivalent internal resistance is given by the sum of the resistances. And in the parallel combination, the equivalent EMF is given by E1 R2 plus E2 R1 divided by R1 plus R2, and the internal equivalent resistance is given by R1 R2 divided by R1 plus R2. The mixed group in which the M rows in parallel combination such that each row contains n cells, each of EMF E and internal resistances R. Then current, equivalent current will be given by product of M and N into the electromotive force divided by the M external resistance plus N internal resistance. Next is the combination of resistance in series. The current flowing through the resistors that are added in the series will be same, and the potential difference is equal to the sum of potential difference of the individual resistors. Suppose there are 3 resistors joined in the series, then the equivalent potential is equal to V1 plus V2 plus V3. Since V is equal to IR, I current will be flowing through them same. So R will come out to be equal to R1 plus R2 plus R3. And in parallel, The potential difference across the resistors will remain same, but here the equivalent current is equal to the algebraic sum of the current across the individual resistors. That is, I is equal to I1 plus I2 plus I3, and that will result in 1 by R. This is the R is the equivalent resistance across parallel is equal to 1 by R1 plus 1 by R2 plus 1 by R3. On the 19th point, we are having Kirchhoff's first law. It has been given for the electric current. According to it, the algebraic sum of the electric currents at any junction of electric circuit is equal to 0, or the current that is entering a junction, say O is a point of junction, the current entering into the junction is equal to the current leaving the junction. Out of convention, we are taking the current that is entering the junction, that is the point O, is taken as positive. I1 and I2, they are entering, I3 and I4, they are leaving, so they are denoted by the minus sign, or I1 plus I2 comes out to be equal to I3 plus I4. So this is according to the law of conservation of charge. The first law is according to the law of conservation of the charge. And in the Kirchhoff's second law, this is also called voltage rule, or it is also called a loop rule. In any closed mesh of electric circuit, the algebraic sum of the EMFs of the cell in that circuit and the product of current and resistance is equal to 0. And this is according to the law of conservation of energy. The next is the Wheatstone bridge. In this, there is an arrangement of the four resistances. Let it be P, Q, R, and S, such that they are forming the arms of quadrilateral ABCD as shown in the figure. Bridge is balanced when potential across B is equal to potential across D, and there is no current flow through the galvanometer. In that condition, P by Q is equal to R by S. The next is the potentiometer, that is also based on the Wheatstone bridge only. It is using the concept that the potential difference across any portion of the wire is directly proportional to the length of the wire, that is given here. And this thing can be used to compare the EMF of the two cells. E1 by E2 is equal to their lengths L1 to L2, and it is also used to find out the internal resistance, since internal resistance is equal to external resistance, EMF upon potential minus 1. So this is proportional to the length, so R can be calculated here.